All right, folks. Well, welcome back. Before we get started with today, just a couple things. There's still a couple of you that need to make sure that you come by and you see me so that you can take the makeup exam. I need to get in contact with you in order to arrange a time for you to come by, come to Zoom and get your exam completed. Okay. And again, I'll try to have that exam back to you by tomorrow, if not by Friday, and so we can talk about it, or you can come by and talk about it with me either on Monday or sometime next week. Okay, so make sure you come by and you see me, folks, before the end of the week. Okay, all right. So let's go ahead then and let's pick up where we left off with yesterday. And so what I'd like to do is I'm going to try to finish up with the lecture today with a little bit of time. Please make sure you look on Classroom. I've assigned an assignment there, a POGIL activity, an activity for you to do for the remainder of the period today, and hopefully get it done. If you don't get it done during the period today, then finish it up and then submit it through Classroom. So make sure you take a look on Classroom. There is a POGIL activity called mole ratios that you'll have to do. So please make sure you get that done and also complete the homework. The homework will be due tomorrow, but the POGIL activity is due this evening. So make sure you get that done. I'll try to get the lecture done within the time period here or a little bit early. I'll try to end it a little bit early and then give you some time to get that POGIL activity done. Okay. All right. So with that said, then let's go ahead and let's take a look at what we have here. We were talking about balanced equations. We're talking about how we can use the balanced equation in order to understand what the reaction is doing. Okay, so we learned that back in chapter 11. Now, what we're doing here in chapter 12 is we're going to take that balanced equation, include into it a discussion of the amounts of each of the reactant products, so that we can essentially use a balanced equation as a type of a recipe, I think, if you want to think about it that way, a recipe in which we can use to make these products. Okay, so, and just like any good recipe, then, if the recipe has to include the ingredients and also the amounts of the ingredients in order for us to be able to make those, to use that recipe and make anything with it. Okay? And so the balance equation tells us the same thing. You need to think of the balance equation then as a set of instructions that you can use in order to make the product, to run the reaction. And so what we're going to do is we're going to learn how to interpret those numbers, and we're going to have to learn how to interpret the balance equation. But once you do, you can then see it as a set of instructions that can be utilized to run the chemical reaction. Okay. All right. So with that said, then we were able to, on the most basic level, you can take a balance equation and determine then how many atoms total are involved in that reaction itself. Now, based on the law of conservation of matter, law of conservation of mass, we know a couple of things. First of all, the amounts of atoms have to be the same. We start out with a certain number of atoms, you have to end up with that same number of atoms. And that's what we learned back in chapter 11. We learned that when we balance an equation, when we balance a chemical equation, we are showing then that that the atoms are the same. When you start out with a certain number of atoms, you can end up with a certain number of atoms. However, the type of atoms also do not change. So if you're going to start out with a certain type of atom, you end up with the same types of atoms as well. You are neither creating nor are you destroying the atoms themselves. And so we learned then from Dalton's theory, Dalton's atomic theory, that when a chemical reaction occurs, basically what happens is the atoms just simply rearrange the order, rearrange the type of interactions that they have. They break bonds and they form bonds. And so new bonds form, old bonds break. And so that's why when we look at a balanced chemical equation, that's what you got to keep in mind first and foremost, and that is the atoms stay the same. You can't, during the course of chemical reactions, the atoms don't change. Neither do they change their number, nor do they change their type. And so when you look at a balanced equation, you have to recognize that first. Okay? So a balanced equation gives us the total number of atoms involved in a chemical reaction. Okay? So with that said, then we were able to interpret the balanced equation yesterday based on what we call the atomic level, okay? The number of atoms that are involved. But we can also take that balanced equation and determine then the total number of particles that are involved, not at the atomic level, but here we're talking about molecules. Okay? And so we use this term molecule somewhat generically. Okay, so you want to make sure you understand that when we talk about the term molecule here, okay, and let me go ahead and do this. when we talk about the term molecule here, the number and type of molecules, we're using this term somewhat generically. Okay, so what does that mean? The term molecule here can refer to molecular compounds. Okay, it can refer to molecular compounds. Okay, but it can also be, it's also used to refer to ionic compounds as well. Okay, so essentially then, when we talk about looking at a balance equation and using the coefficients to indicate the number of molecules, what we are actually referring to is the total number of the total amounts of the compounds. We are analyzing it on and looking at it and trying to describe the number, describing the compounds. Okay? With the atoms, then we're just focusing on a single atom. We're focusing on a single element. Okay? But we can also determine the types of compounds that are involved in a chemical process, in a reaction, as well as the number, how many of each one of those compounds are involved as well. So make sure you understand this, that when we use the term molecule to describe, and I'm going to put the term molecule, sorry, it's not working very well. The term molecule here, and let me clean this up a little bit here. The term molecule here then is referring to, and again, I put this in quotes because it is referring to compounds. It's referring to the compounds that are involved in the chemical process itself. And this is what you have to make sure you remember. Okay, this is what you have to make sure you keep track of when we continue this discussion. Okay. All right, so with that said, the balance equation then will give us the ratios of the reactants and products, okay, in a chemical reaction. Okay, so the ratio, so the coefficients themselves will give us the ratios between the reactants and the products, okay, between reactants and products. Okay? And so we can use that to determine then the number of molecules that are involved in a chemical process. Okay, so make sure you keep that in mind as we move forward. So the best thing to do here is practice this, folks. Let's go ahead then and let's take a look at an example here. Okay? Let's take a look at this particular reaction. We've been working out this reaction together. Okay, so let's take a look at this reaction and let's work this one out together. Okay, so the balance equation here involves nitrogen, diatomic nitrogen, reacting with hydrogen to form ammonia. Okay, so we've already talked about this. This is nitrogen here. This is nitrogen. Sorry, you guys, I don't know what's going on here. Let me try this again. This is nitrogen here. Okay. This is hydrogen here. When they react together, they form ammonia here. Okay. And so we're going to interpret this, and we're going to interpret this equation in terms of the total number of molecules here. And again, when we refer to molecules, we're talking about the compounds. Okay? Let's go ahead and let's take a look at the types of compounds that are involved here. The first, remember, compounds, then make sure you keep that in mind. Compound then is a substance in which you have more than one atom coming together, more than one type of element come together. So here you have two nitrogens coming together to form the compound nitrogen. So two separate nitrogen atoms. And so I drew this for you yesterday. Essentially, then the compound is made up of a triple bond that exists between the two nitrogen atoms. That's the compound itself, and that's how we draw it. So we're not, when we refer to nitrogen here, we're not referring to an individual nitrogen atom. We're referring to this entity right here that we learned how to draw back in chapter 8. Okay, so that's nitrogen. That's the nitrogen that floats around in the air. That's the nitrogen that we need to breathe in, okay? Not the nitrogen atom. Okay, then so that's the compound here. This compound is a diatomic molecule, diatomic compound made up of two nitrogen atoms triple bonded together. This is hydrogen here. Hydrogen, the compound here is made up of two hydrogen atoms that are bonded together, using a single bond. So we talked about this already. Okay, so this is the compound that we are looking at here. Okay, so that is the compound here. Again, a compound is made up of two or more atoms. Okay, two or more atoms bonded together. Okay, and so with that said, there, ammonia is this compound here in which you have three hydrogen atoms. Okay, three hydrogen atoms that are about, let me redraw that for you folks. Sorry, that looks horrible. Let me draw it to the side here really quickly. Okay. So we have then 3 hydrogen atoms. So there's ammonia with 3 hydrogen atoms, single bonded to nitrogen. Okay, so we have 2 compounds to start out with, and we form this new compound in the end. If you notice then, what we do then is the nitrogens break this bond, hydrogens break this bond, and they recombine to form this. Again, Dalton's atomic theory, during the course of a chemical reaction, compounds break their interactions, bonds get broken here, and then new bonds form. Okay? And so the question then is, if you take a look at how the equation is balanced, if you take a look at how the equation is balanced, okay? You have then 1 here. That's understood to be 1. So there's nothing here. If there's no number written here, it's understood to be a 1. So let's go ahead and write that in for you right now. Okay. So it's understood to be a 1 right here. Okay. So with that said, then we have 1 particle, and this is the way we can interpret the balance equation. 1 particle of nitrogen. 1 particle of nitrogen. There we have it, reacting with 3. So if you take a look at here, 3 particles of hydrogen. So how would we represent that? Well, we'd have then 1 second, and then a third. So then you have 3 particles of hydrogen reacting with 1 of nitrogen. Okay, and so with that said, how can we interpret the 2 on this side here? Well, when you take 1 particle of nitrogen, and you react with 3 particles of hydrogen here, you're going to form then 2 ammonias. Okay, 2 of these particles will form. That's what the balance equation gives us. That's what the balance equation gives us. And so with that said, then we can draw on this side here then, and I'm just going to draw it real quickly then, and I'm sorry, I should have drawn it down here. But you can imagine then we start out with 2 of these, okay, 1 of these here, so we have reactants, so we have 1 particle, and instead of writing out everything, you don't have to draw out the Lewis dot structure, but you do have to recognize then that we start out with 1 particle of nitrogen, this here, which is made up of 2 nitrogen atoms together, and so we write it as N2. We start out with 3 hydrogens, okay, and so we end up with then, based on the balance equation, 2 ammonias, okay. All right, so make sure then that you understand what we have here, okay. So, and if you notice here, if you add up the total number of particles here, you have 4 particles to start out with, 4 total particles, 4 total molecules, okay. So let me go ahead and erase that real quickly. Okay, so we have 4 molecules to start out with. Okay, so we have 4 here, 1 nitrogen and 3 hydrogens, 4 molecules to start out with. But if you notice then, we end up with only 2 molecules produced. And so there is no conservation here. That doesn't mean the law of conservation doesn't apply. But again, the law of conservation applies to atoms and also to mass, which is what we'll talk about in just a moment. Okay? All right, so make sure you keep that in mind on what we have here. So what I would like to do then, and let me go ahead and clear this up. I'd like you to try a problem here really quickly. Okay, and let's take a look at these 2 here. Okay, so now that we've learned about this, I want you to take, let's do number 14 in your problem set. Take a couple minutes to do a few minutes to do this. I want you to take both of these reactions here, the first reaction and the second reaction, and I want you to interpret both of these reactions in terms of atoms, and total number of molecules. Okay? And so go ahead and do that. Okay, and then we'll go over this real quickly. Okay, and then we'll continue on. Okay, so take about 3-4 minutes, okay, to interpret both equations in terms of atoms and in terms of molecules. Okay, so go ahead and do that, folks. Okay. All right, let's go ahead then and let's take a look at the first one. Okay. All right, so with that said then, we want to interpret it in terms of atoms and in terms of molecules. So in this table here, I have drawn out for you, okay, what we have here. Okay, so let's count atoms first. So we're going to count individual atoms. So we're not going to look at the total particle here. The very first level, we're just going to count atoms, okay. So sodium atoms, so we're going to count sodium atom. Sodium atom only appears in this compound here. When this coefficient is placed in front of this compound, it tells us that we have 3 sodium atoms, 3 individual atoms of sodium. Okay. On the left-hand side here, we also have iodine. Okay, so we have iodine there. Okay, and the number in front of that compound tells us that we have 3 iodine atoms to start out with. Okay, all right. So that accounts for the total number of these 2 atoms here. Okay, let's go to the next one, hydrogen. Okay, so we have hydrogen. We start out also with hydrogen, and this subscript here, this little number here, tells us that we have 3 hydrogen atoms to start out with. Okay, we also have phosphorus in our reactants. Okay, so we have phosphorus here, no subscript, no coefficient. The coefficient here is going to be 1, sorry, which means that we only have 1 phosphorus particle atom. Okay, and then finally with oxygen, we also have oxygen in the beginning. Okay, and so therefore then the 4 here tells us that we have 4 oxygen atoms. So let's add up everything, all the atoms here, and let's see how much we have. We have 9, 10, we have 14 total atoms. We have total of 14 atoms to start out with. Okay, so those are our reactants. Let's jump over to the product side here, and let's do the same thing. Okay, starting out then here, we have 3 hydrogens. Okay, I'm sorry, let's start out with sodium. Okay, so here's sodium. Okay. And if you notice that there's a little subscript here next to sodium with 3, which tells us that we have 3 sodium atoms. Okay, let's count iodines. The iodines are here. Okay, so this is part of a new compound here, but it's iodine is right here. And the coefficient in front of this compound tells us that we have 3 iodines. Okay, let's find the hydrogens and count those. Okay, so hydrogen is here. And again, the 3 in front of the hydrogen tells us that we have 3 hydrogen atoms as well. Let's continue on. Let's count phosphorus. Let's go ahead and find phosphorus on the right-hand side of the arrow here. There's your phosphorus. No coefficient here, no subscript here, which means we only have 1 phosphorus atom. And then finally with oxygen. Okay, oxygen's right here. We have 4 of those. Okay, as well. And so let's total up all of these atoms, and you notice then that we have a total of 14 atoms as well. 14 atoms as well. So we have conservation of atoms here. Okay. All right, very good. So those are atoms. Let's go ahead and let's take a look at the molecular. Let's count molecules in. So the very first molecule that comes up then is the sodium iodide, this compound here. The coefficient in front of that tells us that we have 3 particles of sodium, 3 sodium iodide molecules. Okay? And again, I use that term molecules in quotes because this is not a molecule. Obviously, this is not a covalent compound. This is an ionic compound. But again, we are using that term molecule to simply describe compound. Okay? So the very first compound here is sodium iodide, and we have 3 of those. The second compound here is phosphoric acid, H3PO4. If there's no number in front of it, we can see then that the coefficient is going to be 1. So the total number of compounds here then is going to be 4 total. Okay, when we start out with. Okay, all right. So going to the product side then, let's identify what compounds form and how many of them form. So the very first one here is HI, which is hydroiodic acid, and there are 3 of those that form. Okay. And then the second compound that forms then is going to be Na3PO4, sodium phosphate. And we have 1 of those that form. Okay, and totaling this up here, then we have 4 total atoms, 4 total compounds that form. And so in this particular reaction, and it does work out sometimes this way, but it doesn't always work out this way, mind you. Okay, but in this particular reaction, the total number of particles also are the same. So if you notice here, the total number of atoms on both sides is 14. We have 14 total atoms, but we only have 4 total particles on both sides. And when we talk about particles, we're talking about the atoms, the compounds. The atoms interact with one another. So at the very most basic level, we're counting individual atoms. And at the very next level up, we're using the balance equation to find then the number of molecules, the particles, that the compounds that form. Okay. All right, very good. Let's go ahead then, and let's let me go ahead and clear this up. Let's go ahead and do the next one. Okay, let's do the same thing for the next one. Okay, and hopefully you were able to do this as well. Okay, if you need to draw out these tables, go ahead and do so, folks. Okay, so let's go ahead and let's start out atoms. Okay, so let's start out and let's identify the first one. We have potassium, and on the reactant side, on the left side, we have 2 potassium atoms. We have oxygen next. Okay, and how many oxygen on the left here? We have 1. And then we have 2. We have 2 oxygens as well. Okay? Two oxygens. Okay? And then finally, hydrogen's the only other atom found on the left-hand side of the arrow is hydrogen. And we have 2 of those, okay? So a total of 6 atoms total to start out with, okay? So we have 6 atoms total. Let's go ahead and take a look at the right-hand side. So again, on the product side, we have potassium, and this coefficient in front tells us that we have 2 potassium atoms, okay? We also have oxygen on the right-hand side, and again, that coefficient tells us that we have 2. Then we have hydrogen also on the right-hand side, and this coefficient tells us that we have 2 as well. So we have then a total of 6 atoms. 6 atoms on the right-hand side as well. So the total number of atoms have to balance out, okay? So we've counted individual atoms. Let's go ahead then and count molecules, okay? Count the compounds, okay? So we have then potassium oxide. We start out with potassium oxide, and we have 1 of those, okay? We have water, okay? And we have 1 of those, okay? And so we start out with 2 total molecules, okay? We start out with 2 total molecules, and with that said, then we have potassium hydroxide, KOH, forming, but this coefficient in the front tells us that we have 2 of those, okay? And so therefore we have also 2 total molecules that form. So here, we start out and we end up with the same number of molecules, okay? But understand that will not always be the case. It just happens that the 2 examples that we have here shows us that, okay? All right, let's go ahead then and let's continue on. Okay, so practice that, folks, and make sure you're able to do that. Okay, so make sure you practice that. Okay, let me go ahead and clear this out. Okay, all right. So we can discuss then, we can talk about then how the balance equation gives us the total number of atoms. The balance equation also gives us the total number of molecules that are involved. But understand this, when you run a reaction, you don't run it, you don't carry out a reaction at the atomic level. You don't take individual atoms and mix them together and get them to change. That's impossible to do. Furthermore, you cannot take individual particles, individual molecules, and combine them together to form your product. That's not very practical either, and that's not doable either. Okay? So what are our options then? Well, we have to scale it up to the macroscopic level. Okay? And so that means we have to measure out, or we have to count out a certain number of particles, a certain number of atoms that will work for us here. And that is, we have to scale it up. And how do we scale it up? How do we scale up the particles here? Well, we talked about this. Okay? We have a unit here known as the mole. We have the unit known as the mole here. And remember, the mole then indicates then not just one particle. Okay? A mole, and let me try to finish up here, indicates then this many particles, 6.02 times 10 to the 23rd, okay? And so what I would like to do tomorrow then is use this relationship here and use that to, in the context of a chemical reaction and the balance equation, and use that to determine then to count the number of reacted particles and the number of product particles, and to compare those, okay? And so we'll do that tomorrow. What I'd like you to do now then is to finish up by taking a look at the POGIL activity. Please take a look at the POGIL activity, okay? And to get started on that. And then you'll submit that. Make sure you submit the written work for the lecture here. But make sure then that you submit the POGIL activity, get that started right now, okay? And work on it until the end of the period. If you don't get done by the end of the period, please make sure you get that done for homework. I assigned set A from chapter 12. Please try that. It's not due till tomorrow, but please try that, and then I'll finish up with the material that you'll need to get that done. But please get that done for tomorrow. And if you have any questions about that homework assignment, please make sure you stop by today after school, 1:30 to 2:30, to ask about that. Yeah, so make sure you come by after school today to get your questions answered. Okay. All right, folks. So please get the work done, and then I will see you tomorrow. Okay? Have a good day.